Right, so this is going to be a demonstration, just an audiovisual presentation of the UBD project that includes the math EEOs, which is just kind of naturally fits into the um, physics lessons anyway. This is not the same lesson that I was doing previously because I didn't see a good way of fitting that in. This is instead a follow-on to a previous lesson I did. I'm going to be doing this simulating with a docu-cam, kind of a wonky, janky contraption set up on my desk. Uh, so I'm going to do this simulating as though I'm teaching it to a class, and pretending as though there's classroom engagement, even though I'm actually on my own. So here goes. So hello everyone, this is day 2 of the friction content. Today's going to be a little less exciting than what we did yesterday with all the running around, sliding with our socks, and sliding blocks across surfaces and all that stuff. Today we're just going to be kind of going back a little bit to the just kind of the more mathy sides and just seeing applications of this in some of the kind of problems you might see. So a little less fun, a little less experiential, but still important. So let's just go ahead and get right into it. So our first problem, so we're looking at the friction stuff, and the ideas we learned in class yesterday. So our first problem, you should all have handed all these worksheets out to all of you. You should also have your equation sheets and notes at the ready. So the first problem says, a car stops as quickly as possible from a speed of 100 kilometers per hour, the driver pressing as hard as they can on the brake pedal and anti-skid activating to prevent tire lockup. Its tires have a coefficient on a dry road of mu static of 0.72. What is the stopping distance? All right, so how do we go about this? Any ideas? Any first thoughts? Jimmy, you got anything? Oh yes, friction. Yes, that's the equation we had from last time. So force of friction is equal to mu times normal force. All right, and can anyone tell me what the normal force is? Billy? Yeah, it's the weight. So normal force is equal to the weight, and that it would be mass times gravity. Yes. Thanks, Josh. So mass times gravity. So we put that together. We have mu is equal to, or force of friction is equal to mu times m times g. So what else do we have going on here? So that's our force of friction. So what else is going on here? So we so yeah, Alex, yeah, that's we have acceleration is we have we're going to be dealing with acceleration because we have a speed, a change in speed, and a change in distance. And this is just kind of going back to some of the 1D. See if I can get this to stay. The 1D motion that we went over earlier in the semester from our equation sheet. It's kind of hard to see on here, but we have our S minus S naught is equal to, or V squared minus V naught squared is equal to, well, we're talking about a speed and a distance, so we'll use this one, constant A naught, because acceleration is constant regardless of speed, acceleration from friction, or deceleration in this case. So we have V squared minus V naught squared. We know that one of the speeds is 0, so we'll just have V squared is equal to 2A times S, which is our distance. So we have our V and our, so the two things we need to know here are our V and our A. So our V, we know that we're going from 100 kilometers per hour to 0 kilometers per hour. Let's convert all this to meters per second. So anyone tell me how to do that? Hannah? Yeah. Okay, yeah. So we have 100 kilometers per hour We'll use dimensional analysis. Yeah, so that's 1,000 meters per kilometer divided by 3,600 seconds per hour. So it's a fancy one, as we just said, all from earlier. Does anyone want to punch that in? Actually, I'll just do it on my calculator here. So we have, I can't even really see that. We have 100 times 1,000 divided by 3,600. So that gives us 27.7. We'll just call it 27.8 for rounding. You notice 2 sig figs, so we'll go with we'll just use 3 sig figs for this part. 27.8 meters per second equal to V. All right, so that's one part. Might not have given myself enough space on this. So that's, we'll circle that. So what's our A? So A, we know, anyone give any suggestions as to what, oops, go back to my camera here. So we know that, so we have our 27.8 meters per second is our velocity, our initial velocity. What's our A? We know that acceleration is equal to, Amelia? Yeah, yeah, good call. F equals ma, which can be rearranged as A is equal to F over m. So we know our force. Force is equal to so A we can substitute in. We know that force from friction is equal to mu times m times g, and this is all over m. And one thing, but we have a little bit of an issue here with plugging things into this equation. What's the mass of the car? Well, it's not specified. I don't know, probably anywhere from 1 to 3 tons, but we're not given a mass. Does anyone have any ideas of what we can do with that? Or do we need the mass? Can we solve this problem without the mass? And you look a little confused. No, you say we do need the mass? Well, actually, I'm going to go ahead and say that we don't. You notice that looking at it from the equation part here, we notice that we have a mass on the top and a mass on the bottom, so they cancel. So that gives us an acceleration of is equal to mu times g. So this is our acceleration equation. And let's just think about this intuitively for a moment. That's so you can see it on the screen. Think about this intuitively. We know that friction is proportional to weight, which is proportional to mass. We also know that acceleration is inversely proportional to mass. So if you were to combine both of these factors, you're going to combine both these pieces of information, you'd notice that if you have more mass, you have more friction, but also more mass to decelerate or accelerate. So they end up kind of canceling out. So acceleration from skidding and friction is independent of mass. So let's so now we have our A and we have our V, so we can plug this in. We have this V squared is equal to 2A times S over here. We can try to rearrange that to get S by itself. So S, move the 2A over the, divide both sides by 2A. So we have S is equal to V squared over 2A. We can plug in our numbers. So that's equals 27.8 meters per second squared, or meters per second, that whole thing squared, all divided by 2 times 9.81 meters per second squared times was this 9.1 meters per second squared times our mu, which is 0.72. So we can run this through a calculator. 20, show my calculator, 27.8 squared divided by 9.81 times 0.72. And that gives us 109.4. So we have 109.4, and let's see what our units should be. And because we're looking at distance, we should be getting a distance in meters. But let's see. So we have the seconds squared here. So remember that the squared distributes into both of these. So we have a second squared on the bottom, a second squared on the top. That's a unitless ratio. Mu is a unitless ratio. 2 is a unitless coefficient. This meters gets squared. This meters is not squared. So we have that one of that cancels, or so that cancels with one of that, and we're left with meters. So our dimensional analysis checks out. We have, I'll just write a little bigger, 109.4 meters is our stopping distance. So any questions about that? Follow along. And a couple blank stares there, but I think most of you are understanding. Just don't be afraid to speak out and ask for help. I can't. Jimmy? Oh yes. All right, what was the question? Hard to simulate this without actual questions from students.